Good day, listeners. In today's lecture, we shall talk about the concept of bounded subsets, where, as we know, R denotes the set of real numbers. In this discourse, very important notions, two very important notions will be discussed. The notion of infimum. As we proceed in this lecture, these two notions will be dealt with. And I will do my best to make sure that everything about them will be simplified. They are, to me, perhaps the most important concepts in mathematical analysis. The notion of infimum and supremum. They are the most important to me, that's from my own little understanding, the most important concepts in mathematical analysis, because with them, several other important concepts will be developed. For example, with them, we'll see that, for instance, a monotone increasing sequence that is bounded above will converge to its supremum. Monotone decreasing sequence bounded below converge to its supremum. With this, we can also develop the notion of Riemann integration, that is, given a function with the two notions of infimum and supremum. We'll know when the function is Riemann integrable and when it's not. So these are two notions that we must pay serious attention to. And for us to derive the message from, we'll start as follows. We'll start with the following definition. Let A be a non-empty subset of R. There is a non-empty subset of the set of real numbers. A point, say A naught in R. So once these two properties are satisfied, A naught will be called the minimum point of A. And the minimum point of A is abbreviated min A. So we may write A naught equals the minimum. This stands for the minimum of A whenever it exists. A naught is defined as min A whenever it exists. So for a set to have a minimum, it means that there must be a point in A that satisfies condition 2. A naught in A and A naught satisfies condition 2. A point B naught in R is called the maximum point. So again, whenever a set A has a maximum, and that maximum is denoted as max A. So in that particular case, we shall write B naught equals the maximum of A. This is the abbreviation for maximum of A, provided I and II are satisfied. Examples. Let us consider -1. Consider this set. Observe that -5 belongs to A, and that for any other point A we pick in A, -5 is less than or equal to A. Thus, minus 5 equals the minimum of the set A, the A we've just put down here, because the two conditions in the definition of the minimum are satisfied. A contains minus 5, and minus 5 is smaller than every other thing in the set A. Therefore, minus 5 is the minimum of the set A. Observe also that the number 6 belongs to A, and that for any A we pick in A, that A we picked is less or equal to 6. So this means that A contains the number 6, and that number 6 satisfies the inequality that every other point in A is smaller than or equal to 6. So therefore, 6 is equal to the maximum of the set A, where A is as defined above. Let's look at another example. Consider the set, say E, equals the interval, say 2, 5. The closed open bounded interval 2, 5. Recall that 2, 5 is equal to the collection of all x in R, so that 2 is less or equal to x, while x is really less than 5. By this definition, we'll see that 2 is a member of the set because 2 is inclusive, while 5 is not, because every member of the set is strictly less than 5, but greater or equal to 2. So 2 is a member. But by this definition, we shall see, by this definition, it is easy to see that 2 is in E, and that for any x in E, so what we are saying is that for the set E equals to 5, 2 belongs to E, and for any x in E, 2 is less or equal to x. Thus, 2 is equal to the minimum of the set E. Now, let us look at the other end of that particular set. I want us to observe, on the other hand, observe that for any x we pick in E, where E is defined above, where E is 2, 5, the interval 2, 5. For any x we pick in E, x is less than, or I can say x is really less than 5, which I can say implies that x is less or equal to 5, because the truth statement is the one we pick. X is less than or equal to 5. But 5 is not in E. But 5 is not in E. Thus, 5 is not the maximum of E. In fact, that set E has no maximum. The reason is because if we assume that E has a maximum, say y naught, then if we assume that E has a maximum, it has a maximum point, say y naught, then y naught must be in E, and for any x we pick in E, x must be less or equal to y naught. This is a necessary thing that must happen if y naught is the maximum point of E by our definition. But looking at E, remember that the set E is the set from 2 to, say, 5. So we are talking about all the elements lying within that interval, within the line from 2 to 5. 2 inclusive, but 5 not inclusive. So if y naught must be the maximum of this set, that y naught must be a member of this set, meaning that y naught must be strictly less than 5. And if y naught is really less than 5, let us assume that y naught is here. If y naught is really less than 5, you will observe that this is it's not possible for us to say that y naught is the maximum of the set, because for the fact that y naught is really less than 5, if we take the midpoint between 5 and the y naught, assuming that we take a point here, the midpoint between 5 and y naught, that midpoint will be given by, say, y naught plus 5 all over 2. If we look at this particular point, this point is between y naught, is bigger than y naught, but also slightly less than 5. Meaning that this point is in the set E, and yet this point is bigger than y naught, contradicting the fact that we say that y naught is the maximum. So what it means is that the set E equals 2, 5 has no maximum point. Has no maximum. That is, there is no value in E that will serve as its maximum. Because, assuming that such happens, we'll get to this contradiction. Now, similarly, using the similar argument shows that the set, say, J equals the interval AB, which is equal to the interval AB, if we recall our notation when we introduced the notion of intervals on R. This particular J, let me say, similar argument shows that a set of the form J equals this has no minimum, and has no maximum. It has no minimum and it has no maximum. The reason is clear. The reason is because if we look at the line, as I've shown before, assuming that here, remember, whenever we write this kind of thing, is an assumption that A is really less than B. So if we have here as A and somewhere here as B, we will see that A is not a member of that set and B is also not a member. We are talking about all those points that strictly lie between A and B. So in the same way, assuming that we say that there is a minimum point, then it means that that minimum must be inside this set, maybe somewhere here, meaning that that minimum is an element, and if it's an element, by virtue of being an element of that set, it must be really bigger than A, but must be less than or equal to everything in the set. Now, considering that particular minimum, assuming I call it, say, alpha naught. If I take A plus alpha naught over 2, I will get a number that is bigger than A, but less than alpha naught. And for the fact that it's bigger than A and less than alpha naught is automatically less than B. And therefore, that number belongs to the set J and must lie somewhere here. In that particular case, the assumption that the set AB has a minimum alpha naught is contradicted, because there is another point that is smaller than what we are calling the minimum. So that such set has no minimum and has no maximum. So these are things we should bear in mind. There are so many other examples. For example, another example is the following. If we consider the set, this set N, it is clear that I1 belongs to N. I, for any N we pick in N, for any natural number we pick, 1 is less or equal to that natural number. This means, therefore, that 1 is equal to the minimum of the set of natural numbers. However, the set of natural numbers has no maximum. Because if you assume that it has a maximum, say n naught, it means that n naught, assuming that we take n naught to be equal to the maximum of n, then this means that I'll put question mark because of the awkwardness of that statement. If n naught equals maximum of n, then n naught must be a member of n. And any n in n, for any n we pick in n, for any n we pick in the set of natural numbers, n must be less than or equal to n naught. But this is not possible, because if we take n naught in n, then by the property of the natural numbers, n naught plus 1 must also be in n. And we know that n naught is less than or equal to n naught plus 1. In fact, n naught is really less than n naught plus 1. Meaning that we've gotten n naught is really less than n naught plus 1. So what this signifies is that n naught is really less than n naught plus 1. What this signifies is that this statement is not true, because there is no way every n in n will be less than n naught, and yet we find another one in n that is bigger than n naught. This leads to the assumption that this happens will lead to this contradiction. So n has no maximum. So the one thing I want us to pick from here is that if a subset, say E of R, has both minimum and maximum, say alpha naught equals minimum of E, and beta naught equals maximum of E, then we will observe that 1, alpha naught is in E, beta naught is also in E, and furthermore, for any x we pick in E, alpha naught must be less than or equal to x, and x must be less than or equal to beta naught. This is a fact from the definition of minimum and what? Maximum. This brings about an interesting property of a set that has both minimum and the maximum. That property is that there is a number that is smaller than or equal to everything in the set. And there is a number that is bigger than or equal to everything in the set. This means that I can call the set a bounded set. And this will lead us to the next definition, to the introduction of what a bounded set means. But before we go into that, let us note that whenever alpha naught is less than or equal to every x in E, then what that means is that alpha naught is a lower bound of x. And in this case, beta naught will be called an upper bound of x. But that is by the way for now. We will now go into detail to discuss the concept of lower bound and upper bound. Now, let us take the following definition. Let E be a non-empty subset of R. The set E is said to be bounded below if there exists a number, say theta, in R, such that for any x you give me in E, theta will be less than or equal to x. And the set E is said to be bounded above if there exists, say, gamma in R such that for any x you give me in E, x will be less or equal to gamma. So if I draw, let us look at the set of real numbers R. And assuming that here is the set E, please note that E is not necessarily an interval. Now, the set E is said to be bounded below if I can find a number here, a point here, which I call theta. Theta is that point. So that for any x I pick in this E, theta is less or equal to x. And the E is said to be bounded above if I can find a number gamma in R, so that for any x we pick in E, remember points in E are within here, but remember that as I said, E is not necessarily an interval. So for any x we pick in E, E is less or equal to gamma. When this happens, we say that E is bounded above by gamma and is bounded below by theta. Now, a set E, if a subset of R, if a subset E of R is bounded both below and above, we say that E is bounded. Thus, a bounded subset of R is a subset of R that is bounded both below and above. That is why I made a remark here when I talked about the maximum and minimum of a set. Once a subset E has both maximum and the minimum, then automatically this condition holds, because that minimum will be a member of the set. And not only that is a member of the set, that minimum must be less than or equal to x for all x in the set E. And the x will also be less than or equal to beta for all x in E, where beta naught is the maximum. So any set that is bounded, any set that has a minimum and a maximum is automatically bounded both below and above, and thus a bounded set. So we've seen what it means for a set to be bounded and what it means to be bounded below as well as bounded above. Bounded below means we can find a number. Please let us be careful here. The number that exists is in R and not necessarily in E. There exists theta in R so that this happens. Here, there exists gamma in R such that this happens. So, the number gamma is not necessarily in R. The set E is bounded below if we can find a number theta in the set of real numbers, so that theta is smaller than everything in E. Smaller or equal to everything in E. And is bounded above if we can find a gamma in R, so that for any x we pick in E, x is less or equal to gamma. I want us to quickly make the following observation. But remember, once E is bounded below and above, then E is called a bounded set. Now, if E is bounded below by theta, then theta is called a lower bound of E. And if E is bounded above by gamma, then gamma is called an upper bound of E. But I want us to note quickly that going back to this picture, once E, let me draw it here. Let me repeat the diagram again. We have this, and we have, assuming that here is the set, assuming that here represents the set E, theta, a number here, theta will be called a lower bound of E if theta is less or equal to everything in E. And the number gamma is an upper bound of E if everything in E is less or equal to gamma. But I want us to observe the following. Observe that once we establish existence of a lower bound, then every number, any other number that is smaller than the lower bound you've identified is also a lower bound. Assuming that theta is a lower bound, then we have, say, theta prime less than or equal to theta. We shall see that for any x in E, theta prime is less or equal to theta, less or equal to x, which implies that for any x we pick in E, theta prime is less or equal to x, meaning that theta prime is also a lower bound. That is to say that E is also bounded below by theta prime. So what this means is that once we establish the existence of a particular lower bound, or once we establish that the set E is bounded below by, say, theta, then E is also bounded below by every other number that is less or equal to theta. Meaning that the existence of a lower bound implies the existence of infinitely many lower bounds. The same thing is obtainable for an upper bound. Once a set E is bounded above by the number gamma, every number, any other number that is bigger than or equal to gamma automatically becomes an upper bound. Say if this is a gamma prime and gamma prime is bigger than or equal to gamma, we have this. And this means that any x we pick in E will satisfy this, meaning that x in E, x will be less or equal to gamma prime. And therefore, gamma prime is also an upper bound. This means that once an upper bound is established, every other number greater or equal to the established one is also an upper bound. And meaning that that upper bound, the set E will be bounded above by that number. So you see that existence of a lower bound and the existence of an upper bound will only guarantee that the set E is bounded. And once we have one lower bound, there are infinitely many lower bounds. Once we have one upper bound, there are infinitely many upper bounds. In this particular case, there is something important that we must note, and that is nothing but the fact that once we establish the existence of a lower bound, we shall be thinking about the lower bound that is closest to the set E. If we establish the existence of an upper bound, we shall also be talking about the upper bound that is closest to the set E. Those two upper bounds, the lower bound, those two values, the lower bound that is closest to E and the upper bound that is closest to E, when they exist, are the meat in the soup we are cooking. And that particular soup we are cooking is the soup of understanding the concept of infimum and supremum. The lower bound that is nearest to the set E shall be called the greatest lower bound. And the one that is the upper bound that is closest to the set E shall be called the least upper bound. The least upper bound. That greatest lower bound is what we shall call the infimum, while the least upper bound is called the supremum. So you see, for the fact that we have many lower bounds, if you look at the other, there is one that is greatest of all of them. That one that is greatest of all of them is the one that is closest to the set A, out of all the lower bounds. The same with the upper bounds. The upper bound that is closest to the set A is the least of all the upper bounds. And these two we should carefully characterize because they are very important in what follows. Now, this explanation leads us to the concept of infimum and supremum. Infimum and supremum. But before I go into this concept, let me give some examples so that people may appreciate what we are doing. Let us take some examples. Let us consider the set E equals, say, -5, 2. This open bounded interval, -5, 2. Recall that this interval is equal to the collection of all x in R, so that -5 is less than x and x is less than 2. So by definition of this interval, it is therefore clear. We have therefore that for any x we pick in E, where E is as defined, -5 is less than x. And then x is less than 2. What this means is that this interval is bounded below by -5 and bounded above by 2. Observe that here, -5 is not a member of the set, and 2 is also not a member of the set. That is why we emphasize above that the lower bound is not necessarily in the set, but must be a member of R. So here what we can say is that, thus, there exists -5 in R, so that for any x in E, -5 is less or equal to x. I can write this because since -5 is really less than x, if I write this, it doesn't destroy MFM. I will explain why. Thus, -5 is less or equal to x. -5 is less or equal to x. Thus, the set E is bounded below. The set E is bounded below. Of course, it's clear that the set E is also bounded above because there exists 2 in R, so that for any x we pick in E, x is less or equal to 2, meaning that the set E is bounded above by 2. Now, the problem here is that a listener may be confused somehow, that I have here that minus 5 is really less than x, and here I wrote that minus 5 is less or equal to x. Why is this true? Why can I do this, even though we know that this is the correct thing? The reason is because if we look at this picture, let me put it here aside. If we look at this picture, assuming that here is the point x, minus 5 falls somewhere here. This means that this is a situation whereby minus 5 is really less than x. Now, if I look at the situation like this, if we look at the following diagram, and I have, remember here, that minus 5 is still less than x, means that x is not inclusive. Then here, and I'm talking about minus 5 here. So if I now consider if I consider all the points below x, without x, you see that minus 5 is really less than x. But if I consider the collection of all points below x, with x inclusive, and minus 5 is here, you see that here that minus 5 is still less or equal to x. What does this mean? This means that the collection of all points that are really less than x will be members of the collection of all points that will be less than or equal to x. So writing that minus 5 is less or equal to x is not wrong, because here we choose the one that satisfies what we are talking about. Now, we look at another example. Consider the set, the point that contains only 3 points. This particular set is bounded both here. E is bounded both below and above. E is bounded both below and above. Observe that the number, say, minus 2 belongs to R, and for any x you give me in E, minus 2 is less or equal to x. So minus 2 is a lower bound of E, meaning that E is bounded below by minus 2. On the other hand, 6 is a number in R, and for any x we pick in E, x is less or equal to 6. So E is bounded above, because everything in E is smaller or equal to 6. So the set E is bounded below by minus 2 and bounded above by 6. Thus, E is a bounded set. Because recall that a set is bounded if it's bounded both below and above. The interval, say I equals 2 plus infinity, is bounded below but not bounded above. But not bounded above. This can be seen by looking at here. This is 2. This is the interval in question. So here, 2, and every number smaller than 2 is a lower bound of this set. So this set is bounded below by 2 and every other number that is smaller than 2. Meaning that 2 and all the numbers smaller than 2 are lower bounds of the set. But as the diagram goes, we'll see that, let me hand wave here, that this set is not bounded above, because we cannot find a number in R so that everything in this interval will be smaller or equal to that number. So this set is bounded below, but not bounded above. Okay. Now, recall that if a set is bounded below, then it has infinitely many lower bounds. And this makes it possible for us to talk about the greatest of all the lower bounds. And this greatest of all the lower bounds must be given a special treatment, because that's the lower bound that is nearest to the set in question. The same thing with a set that is bounded above. A set that is bounded above has an upper bound, and thus has infinitely many upper bounds. Once an upper bound is established, then every other number bigger or equal to that established one is also what? An upper bound. Therefore, we can talk about the least upper bound. The least upper bound is the one that is closest to the set. Remember, not necessarily in the set. Not necessarily in the set. Now, at this juncture, I think it's time for us to go further to look at the concept of infimum and supremum.